Hi, and welcome to Haskell Cat, the video series in which I'll talk about Haskell. The cat part is not a pun on category theory, I just really like cats. Alright, so I created this video series to talk about stuff about Haskell, and so today I want to address the issue of how to report errors in Haskell, because there are two very different mechanisms to do so. You can either use a value-based representation, like maybe or either, but there's another way which is not visible in the type system. We can also just decide to throw an exception. So why would you use one versus the other? There are some people in the community that argue that we should never use exceptions and we should stick to total functions, and if our functions can fail, then it should be visible in the type of the function. And so today I just want to examine the ways in which those two error reporting mechanisms differ, so we can figure out whether one is better than the other or whether they're simply useful for different cases. So let's look at a couple of examples where the standard library chose one way or the other. Dividing by 0 chose an exception. Getting the tail of an empty list, or in this case the tail of a one element list, chose an exception. Reading a file which doesn't exist, chose an exception. The standard library seems to be biased towards exceptions, so it's weird that people don't like them. The lookup function to find a value corresponding to a particular key in an association list does not throw an exception. This time it uses the value nothing to represent the fact that the key was not found in the list. So association lists are like a poor man's data.map. So if we use a real data.map, which is much more efficient, now we have a choice. Data.map supports both a lookup function, which represents the fact that the key is not in the map using nothing, and it supports the bang operator, which represents the fact that the key was not found in the map by throwing an exception. So here, I'm using the two operators from data.map to implement the same computation twice. It's some silly computation in which I look up a key to get a value, and then I use that value as the key for the next thing, and eventually I get the 4 and I try to look it up and there's an exception. But what I want to demonstrate here is that it's possible with both styles to implement a computation that does several steps, focusing on the happy path, and if there is an error, then it aborts the entire computation. So the two ways to represent errors are similar in that regard. Another way in which the two ways to represent errors are similar is in the fact that if an error occurs, that error it can be bubbled up the hierarchy of calls. So for exceptions, it's quite clear that this does occur, but if we use the do notation, again, focusing on the happy path, the behavior, if there's a failure here, is that this entire function will fail, and so this call will fail, and so this entire function will fail, and so here we will get nothing without us having to do anything to propagate the value. It's just done automatically by the semantics of maybe. And in both cases, as we can see here, I've detected the failure. In the case of the exception here, it's a bit more tricky. I haven't detected the failure. It says it succeeded, and the reason it's doing that is because Haskell is lazy. If I want to make sure that bang plus 2 gets forced and that an exception is thrown, I need to force it using the sec. And so, seeing that the two ways to represent errors are so similar, what are the differences? So we can see here in this implementation that the main difference is at the type level. We can see that when I'm using maybe, the type system knows that I'm using maybe, and so it's making sure that I'm handling the possible error. Whereas if I'm throwing an exception, the fact that there can be an error is invisible, and so the type system is not encouraging me to catch the mistake. So here, lookup plus 2 has type maybe int. If I tried to use lookup plus 2 as an integer instead of acknowledging the possibility of failure by using it as a maybe int, then the compiler is unhappy, it complains, I need to fix my program. So In the other case, if with the exceptions, if I decided to just call bang plus 2 plus 1 without trying to catch the exception, I don't need to do anything. The compiler is happy. It's just going to fail at runtime. And some people think it's bad. But I would like to argue that the fact that the types does not encourage us to catch the exception means that we're not supposed to catch the exception. Types are supposed to help us. They're guiding us towards writing correct programs. And so if I, as the author of a library, decide to give a function which returns a maybe of something, it means I'm telling you the correct way to deal with this error is to handle it immediately, or, to bubble it up to your caller who will handle it. Eventually, some caller will handle it semantically. Whereas, if, as the author of a library, I decide that, oh no, this error, I'm showing an exception, this means that I don't think that the proper way to deal with this error case is to catch and handle it. There's something else that needs to be done. So let's look at a couple of examples. Here, what happens when we divide by 0? It's showing an exception, and so from my newfound understanding of exceptions, it should mean that I don't want to catch this error. So in which way do I not want to catch this error? Well, one reason why I don't want to catch this error is because, well, most of the time, I will not divide by 0, I will divide by some other constant, like 2, and it's much more convenient to be able to just continue my mathematical expression to, in this case, adding 1, without having to wrap the call to divide by 2 using something. Like in this example, right? If I was to use a special version of div called div prime, which instead of throwing an exception, it returned nothing in case of division by 0, then I wouldn't be able to write this simple mathematical expression. I would have to pattern match and see what happens, and if it succeeded, I continue my mathematical expression by adding 1. But this is really silly because since I'm dividing always the constant number 42 by the constant number 2, I know statically at compile time and when I write it that, well, I'm not dividing by 0, I'm dividing by 2, and so it will never be the case that the error will happen, and so it makes a lot of sense to not handle it. Like I claimed, that exceptions are errors you don't want to handle. But that's a very silly example because I was dividing constant. A much better example would be one in which one of the two inputs come from outside, from the user or some database or something, and then under some executions of the program it can succeed, and under some executions it can fail, and so it makes a bit more sense, perhaps, to catch the error. So if it's the numerator which comes from outside, and I'm always dividing by 2, then we have the same case as before, that the error never happens, and so it makes sense to not catch an error that never happens. In the other case where the denominator comes from outside, then maybe the denominator can be 0, and then the error can happen. But I would argue that even then, maybe the correct way to handle the problem is not by catching the error, but by preventing the user from typing 0 in the first place. Maybe we're not asking the user for a number they want to divide, but maybe we're asking them for a number for something else, and it just happens that we're doing a division somewhere. And so if it's semantically incorrect for the user to type 0, then we should give an error message that the user can understand. And we can only do that before performing the computation. So if we do that, if we do this properly, if we catch the error before the division, then again, the division by 0 will never happen. And so it again makes sense to not catch it. Now, before I go further, I just want to talk about one cool project called Liquid Haskell, which is not the focus of this video, but I just want to mention it in passing. Because if we do want to make sure that us programmers don't make the mistake of allowing a division by 0, and we want to check before that the input is non-zero, then the existing mechanism in Haskell are not that good to express in the type of div prime that the second argument cannot be 0. But in Liquid Haskell, they have a extended type system that allows you to write those annotations, like the second argument is v and it should not be 0, and it's able to check at compile time whether we did something like that to detect whether a user typed 0 and ask them to do something else, or if we forgot, then you'd get a compile time error. It's great. And if we don't have Liquid Haskell, then, well, we don't get a compile time error, but it's still our responsibility as the programmer to make sure that we don't allow 0 to get into a code path where it gets used as a denominator. And so if there is an error, if there is a division by 0, it's not that we should handle this exception and print some error message to the user, but rather it's us as the programmer who did something wrong. We failed to check if their number was 0, and we failed to write the code that writes a user-friendly error message before doing the division by 0. So that's why in this case, it does make sense to not catch the exception, because we want the exception to propagate up and to tell us, either via the logs or by crashing our program, that we made a mistake, that we must go and fix the program to detect whether the user typed 0 and print a pretty error message. All right, next example. If we take the tail of a list with only one element, same thing. You know that tail is not supposed to work with an empty list, and so if you are calling tail, it's because you, as the programmer, you are asserting that this list will be long enough. And again, it's something that with Liquid Haskell we could make sure compile time this doesn't happen, and this is great. And in absence of it, we as programmers need to make sure that this doesn't happen, and we need to do so by doing some fancy logic on the input before calling tail. It's not the kind of thing where, oh, I thought this list was long enough, but it turns out it isn't. How do I handle the problem? It's too late afterwards. The next example, lookup and bang. Why do they give us those two different mechanisms? Well, because there are two different ways in which we can use maps. Here's an example in which I want to traverse a directed graph using depth first search. So I'm representing a directed graph as a map from each node to a list of its neighbors. And here in my implementation of depth first search, I'm returning a map from node to the index at which I visited that node. And so I can use that partially constructed map as my set of visited nodes. And when I want to check whether I've visited that node already, then it makes a lot of sense that the result will tell me so using either just or nothing. But when a little bit later I want to look at the list of neighbors of the current node, then it makes less sense, because like if there's a failure, if there's a key which is not in the map, it means that there's a node which has as one of its neighbor a node which is not in the graph. And that's just not a valid graph representation. It means I made a mistake here. If I put an E here, this would make this particular map not be a representation of a graph. And so, well, it's my mistake. I need to go and fix it. It's not something that I can do afterwards to react, oh, well, since there was a mistake, I can, well, what can you do, right? The one thing I don't like is that the message is not super clear. Maybe it would make a bit more sense to use lookup and then to throw this other error saying that the reason why we failed and we need to fix something is because something earlier generated an invalid graph representation. But still, in this case, the API is that the first search is not returning a maybe of something. It's directly returning the map, even though there's the possibility of failure, because if that failure occurs, if there's an invalid graph that was generated somewhere, it's the code's fault for not checking that earlier. needs to bubble up, the programmer needs to fix it. So to summarize what I've said so far, and what I've repeated several times, so maybe it's not really necessary to repeat it once again, but when you are using the maybe or either or some value-based representation of a failure, it means you are telling your users that there is an error that can occur and they should probably handle it now, semantically, because they know what it means for this particular value to be returned. If lookup returns nothing, it means the semantics of this nothing is the key was not in the map. And the semantics of what to do in this case depend on what the caller wants to do. In the previous slide, the semantic was either, oh, we haven't visited yet, let's visit it, or it was, oh, the graph was invalid, let's throw an exception. And when we do throw an exception, what we are trying to say to our callers is, well, don't catch it. If this ever occurs, it means that you made a mistake in your implementation of the algorithm, you didn't satisfy my preconditions, there's no semantic thing you can do with the information that there was an error in your implementation of the algorithm, except aborting, displaying a message, and asking the programmer to come fix it. Of course, it doesn't mean that we should never catch exceptions. If you're a web server, you probably don't want to crash and not serve the web page for anybody else. You probably just want to abort this particular interaction and display a generic error message saying that the programmers are on it, they will fix it soon, don't worry, and to quickly serve the next request, hoping that this one will succeed. Oh, and one last thing I wanted to mention. So I may or may not have convinced you that exceptions are meant for those cases in which you don't need to catch the exception, but it doesn't really matter whether I'm right or wrong because, well, that's the interface we're stuck with. If a function throws an exception, then the type system does not encourage you to catch it. It really doesn't. And so we might as well use those exceptions for those cases where we want to encourage the user to not catch it and to use value-based errors when we want to encourage the user to catch them. It doesn't matter what they were designed for. We are stuck with what we have, and we might as well make the best of it. All right. So for the next part of the video, I would like to discuss the fact that sometimes there's a library that uses the wrong type of error reporting mode. So in this case, there's an association list, and lookup, as we've seen, always returns a maybe of something. But what if I'm not happy with this API? Maybe I really like the bang from data.map, and I'm unhappy that there's no equivalent bang for association list. So I can easily write one by simply calling from just on the resulting maybe of something. And what is the semantic of from just is to convert a value-based error into an exception-based error. And so it's us asserting to the compiler, trust me, according to my algorithm, I know that this will always return just of something. And if I'm wrong about it, if it returns a nothing, like in this case, then an exception will be thrown, and that's what I want to happen. I want the exception to show up in my logs. I want to be told to go back and fix the algorithm. Don't want it to be silently ignored. If I want to go in the other direction, here we had read file foo, which was throwing an exception if the file doesn't exist, and I think that's a good example of a case in which we might want the opposite behavior. I can think of the file system as some map from file name to string contents, and well, I'm not in control of the contents of this tree. It's not as if I put the file there beforehand, and even if I did, the user can have moved it or renamed it or something. And so I don't think that I should trust that the file already exists in any case. I always want to be told about the possibility that the file doesn't exist so that I can handle the nothing and display a nice error message to the user saying, oh, did you move my settings file or something, or you entered the name of a file which doesn't exist. So fortunately, I'm not the only person who thinks that read file and other I/O operations are using the wrong error reporting mechanism. And so there's this library called unexceptional I/O, which allows us to wrap I/O computations with this sync I/O and another few primitives that allow us to, instead of, like in the previous slide, having an exception thrown, you can see that it has been thrown because of those 3 stars in the word exception. If we use sync I/O, now this returns a value left exception, and unfortunately those exceptions are being printed in a way that does not satisfy the usual semantics for show. It does not display as a value, it just displays as its error message. But we can use the REPL. And so if I try to print R, we see this weird left blah blah blah, and that's because if I call show on R, it's that string that does not look like code, and if I want it to look like code, I can use force. This is what should have been used for the show of an exception, but whatever, maybe I'm weird and maybe you prefer the short readable version. Why wouldn't you? So let's move on with the short readable version. So sync I/O is able to catch I/O exceptions that are being thrown by I/O actions such as read file. It does not work with non-I/O exceptions, such as accessing the tail of a tail of only one element. In this particular case, the reason the exception is thrown is not because sync I/O doesn't catch it. As you can see with this modified version, it's because the exception is actually thrown here after the sync I/O block is done. Because of laziness, sync I/O executes the fact that we return something. It just keeps it unevaluated for later, and then now when we try to print it, we evaluate it, and that's where the exception is thrown. But even if I fix the program to force the evaluation of the tail of the single element list so that it fails inside of the sync I/O block, it's still not caught because it's not an I/O exception, it's an ordinary exception. And so I would like to write a function that behaves like unexceptional I/O, but for ordinary expressions. So I want unexceptional to evaluate an expression, and if evaluating that expression throws an exception, I want to return left of that exception, and if it just returns a value, I want to return right of that value. So how might I implement that? So I've used Scala too, not just Haskell, and so I recognize this. This is the same behavior as the try class in Scala, which evaluates some expression, and if that expression throws an exception, it returns a failure of the exception, and otherwise it returns a success of the result. Except that in Scala, you don't have as clear a separation of the side effects as we have in Haskell. Everything behaves as if everything was in the I/O monad, and so a real version of try would have this type. And we do have a version of try in Haskell. It's called try, but it's not the one I want. I would like to do this with pure expressions. The only side effect that they can perform is to return bottom by throwing an exception. And so I can't really do that with a pure expression, because the way in which exceptions are implemented in Haskell, the exceptions are bubbled up through all of the pure expressions until we reach an I/O block. And then inside of this I/O block, the exception is raised, and we can catch it there. And so there's no way I can write a pure expression which catches an exception, because catch is an I/O command, except if I use unsafe perform I/O. So unsafe perform I/O is not to be used lightly. But in this case, I think it's fairly safe, because the only thing I'm doing is evaluating x, and if x is throwing an exception, I will catch it, and it will behave the same every time, and so I don't mind if it gets executed more than once or out of order. So in this case, it's not catching it, it's still throwing the exception instead of wrapping it in the left constructor, and that's the same error as before. I forgot to use sec. And if I do use sec, then I've caught it, I have the left of something. And so that's it. I've implemented unexceptional. I'm happy. Am I? No, I'm not happy, because here's this other example where I'm calling the head of a list, which is not empty, so that should not throw an exception. But this element is itself 1 divided by 0, and so that should throw an exception. And so the exception is caught, left divided by 0, fine. Except it's not really what I want here, because the whole point of implementing unexceptional is that some of the API calls implemented by other people are representing their errors either as a value or as an exception, and I want the other way around. If they implemented it as an exception, I want to be able to switch it to a value using unexceptional. But here, if I want head to behave as if it was returning an error value in case of error, but div to throw a regular exception, then this code doesn't do what I want. It catches the error thrown by a div, even though I want div to throw a real exception. I only want the case of the empty list to be caught as a value representation of an error. So what I want instead is some version of head, which I call head prime, and this head returns either an exception or the head. But if the head of the list contains something that throws an exception, then that exception should be thrown. It should not be caught here. And so this implementation doesn't work because in the two cases I've just described, if I take the head of an empty list, then it is caught, that's good. But if I take the head of a non-empty list, but whose head throws an exception, then it is caught and it shouldn't. So how should I implement this instead? Well, in addition to my unexceptional implementation, which wraps an expression and catches anything that occurs inside it, I will also implement unexceptional 1 for functions of 1 argument, where if there's something in the argument that throws an exception, I want it to be thrown. But if applying the function itself throws an exception, I want to catch it. And I do this by first forcing the argument, and if that still hasn't thrown an exception, then I can apply the function, and this should not cause any other exception than the new ones introduced by f, because if there was something fishy inside x, I would already have thrown it. So this still doesn't work, though, because as you can see, in the case of a non-empty list containing a division by 0, I will still accidentally catch the error. So why is that? There are a couple of reasons. One of them that I'm always careful about, even though in practice it never seems to be a problem, it's that I've used sec instead of a psec. With sec, you don't get a guarantee that x will be forced before unexceptional, blah, blah, blah. You only get guarantee that they will both be forced before the value is returned to the caller of unexceptional 1. In this case, it really does make a difference. If unexceptional blah, blah, blah is evaluated before x, then the exceptions that are inside x might occur inside of my unexceptional block, and then it would be caught, and that's not what I want. So by using psec, which was originally introduced for parallelism, but I never use it for that, I use it for making sure that the left expression, if it returns bottom, and my right expression does something with bottom as well, I want to make sure that the left bottom gets thrown first. It still doesn't fix the problem, because in practice, sec doesn't tend to randomly reorder the arguments. The first argument usually tends to be forced first. It's just not something that is guaranteed by the language. So the real reason why this still got caught is because x is already in head normal form. Because, well, x in this case is this list of 1 element, and forcing it to head normal form it only forces the first cons of the list. So if it was just xs2 equals undefined, then this would throw an exception there. But since it's the cons of something, it evaluates that, and just doing this step doesn't throw any exception. It's only later when I look at the element that it will throw an exception. And so in order to fix that, I'm using the force method from DeepSec, and this will traverse the entire list, so it's less efficient. And so, yeah, it works. It does what I want. And if I wanted to do the other way around, if I wanted head to throw an exception and division to return a value in case of error, I would have to implement an exceptional 2 that does something very similar. And this works as well. All right. So having implemented unexceptional, unexceptional 1, unexceptional 2, and seeing that, oh, it's annoying, there's these issues about laziness, which forces me to traverse the entire structure, and maybe I'm causing some new exceptions that would not have been triggered otherwise, and it's less efficient. My conclusion is that, yeah, there is a problem with exceptions, but it's not the fact that they are not visible in the type and that they bubble up. That is the good thing. That's what exceptions are used for. But there is a problem with exceptions, which is that if a library author decided to use exception, but in your case you would really rather have a value, then it's hard to convert back into a representation that uses a value. So if you are a library author and you're hesitant between returning a value representation of an error or throwing an exception, really the answer is clear. Return a value, because it's much easier for your users to switch to the other behavior if that's the one they want. And if you don't have the luxury of being the library author, if you're a user of a library and the author chose wrong, in your opinion, then you'll have to write a wrapper, which please don't try to do what I did with unexceptional. That was too inefficient and error-prone. Instead, just check for the precondition, and if the precondition is not satisfied, return nothing. So that's what I wanted to tell you today. I have no idea when I'll do another episode of Haskell Cat. It's been like 1 year since my previous video, and it wasn't called Haskell Cat back then. I'm naming the show hoping that it will motivate me to publish videos more often. And so hopefully, see you soon. Ciao.